This talk is on this concept called service discovery, and I'm going to be examining it using Node.js and Consul. I'm assuming everybody here has heard of Node.js. Raise your hand if you've used Consul. OK, 1, 2, 3. All right, 3 people have used Consul. And everybody's probably used Node. Is anybody using other tools for service discovery in their company? All right, sweet. Does everybody know what service discovery is? A few? So service discovery is being able to find services. I guess it was a bad explanation. Like where do your services live? For example, what is their host name and port? How do you find them, etc. And we'll look more into that later. And this content comes from a book I'm writing on microservices. And so here's a URL. I'll show it to you later. And you can sign up for updates if you're into that sort of thing. All right, cool. First, let's look at some different types of static applications. So when I say static, I mean that we're not dynamically finding hosts. And so in this first layer, we've got a request that comes in, and it hits our project. So our project has some sort of web interface to it, and it has data that it's trying to get. Perhaps we're getting data from MySQL database. We're rendering some content on a website, and then returning it to the browser. And so, of course, with Node, we can do that all in a single process. Node can listen for incoming HTTP requests on its own. It's different from other languages, such as maybe PHP, which traditionally didn't have that functionality built in. You'd need a web server. And of course, in layer 2, we can stick a web server in front of Node. And so in that case, we still have our website rendering logic. We still have our data, kind of connected in the same process. And in this third layer, we've pulled the web service and the data service apart. And so now the web service only handles the rendering of the content. The data service handles grabbing data, maybe some model stuff. Comes up with a little API, sending some RESTful stuff over the wire. And so that's what these diagrams represent. But in each one of these cases, we're still doing this sort of static discovery. We have a single instance of our web service. We have a single instance of our data service. And so this approach is fine if you have a finite number of services. If you always expect to have the same amount of traffic, it all works fine. And so in this approach, looking at that third stack where we had things separated out, we did have our web server. We did have our web service or data service. Here we have a simple configuration for our web service. That haproxy.config line. Has anyone used haproxy here before? A few of us, OK. So haproxy is basically a dead simple web service. It's a single binary that you can download. It's written in C. The HA stands for high availability. It can do other cool stuff. For example, routing requests between different backends. But essentially, it's a really lightweight web service. It can do other stuff with maybe TCP connections. It can forward those as well. So if we look at this configuration, we see that we define what is called a front end, and so that represents the requests coming in. So any requests that come in on port 80 of the current machine will end up triggering this, and then by default we send it to the www backend. And so in our www backend, we have a single server instance, which we've named www1. And it statically routes requests to the same instance, the same process. In this case, it's a Node process listening on example.org on port 80. And inside of our service www, this is how we're making outgoing requests to the data service. So in this case, we're simply doing a request.get. We've hard-coded the data service, data.example.org, port 80. We get the content back when you do something with it. Perhaps we respond to a web request coming in. So there's a few shortcomings with this approach. We have a single point of failure in this application. But in particular, the single point of failure is in code that we own. And so, in the world of kind of live fast, break stuff, ship quickly, maybe our applications are not as stable as they could be, whereas something like haproxy is more battle tested. It's used by hundreds of thousands of people. It's had hundreds of thousands of hours of code interaction, or I mean, people contributing, looking for bugs, etc. So something like HA proxy is going to be a bit more battle tested, probably than our code. We are unable to scale these services dynamically. If we want to add more of these data services, we need to manually add their host names to our application code. If we want to add more web services, we need to add them to the HA proxy configuration. So scaling at this point is a manual task. And even if we're using something like Node cluster, so you have a Node master instance that runs and a few slaves that run off of that, the kind of conditions that are going to cause those Node slaves to die are likely the same kind of conditions which may cause our master to die. And so we still end up having these kind of scary points of failure. All right, so now let's look at this thing called Consul. It is an open source discovery tool. It's written by a company called HashiCorp. It's written in Go. It's a convenient, you can actually download it. It's a single binary. Under the hood, it uses the Raft protocol. It forms a quorum, which means you need to have like an odd number of instances running. And what it's doing is it's selecting a leader. So one of these processes is going to be your leader at any point in time. And as long as you have more than half of these instances running at a point in time, you're good. For example, if you have 3 servers and one of them dies, 3 is more than half. I'm sorry, the 2 remaining is more than half. They're able to talk to each other and remain healthy until the dead instance comes back. And essentially, what Consul does is it keeps a list of service instances. And so, the input of this list, you can think of it as like it being a hash. And so you're looking for an instance based on the name, and then you're provided a list of instances that have that name with host and port pairs. It does some other cool stuff as well. You can use it for like distributed, sharing keys of data, like a key value pair. It could do a bunch of other cool stuff under the hood, but we're just going to look at the discovery functionality. Consul also exposes a RESTful API, but you don't really have to touch it. There's a lot of clients out there. And so throughout the slide, we'll actually be using the default Node Consul library. So if you do npm install Consul, you'll get this library. All right, so now we can take that diagram that we have and make it a little more complex. And so in this case, we're going to scale out our data services. So where previously we had a single one, we now have, let's say, 3. You also notice that there's more lines in this diagram. And so the dotted lines represent communication with Consul. And so that communication doesn't represent the main flow of traffic through the application. Like it doesn't represent requests like the solid lines do. These are more, you could think of it as asynchronous requests. And so like, these announcements that we'll look at in a minute are kind of happening on the side. So in this first example, the data service is going to register itself to Consul. The data service is going to have a heartbeat. And so at a predefined interval, we're going to tell Consul that we're still alive. And then the web service is going to be told where the data services are located. All right, so here's some code. This is inside of our data service. This is our Node application. And so this first chunk of code shows how we perform a registration. And so this would happen early on in the life cycle of our application. So early when you start it, probably in the first second or two, once your application boots up, maybe connects to a database, it knows that it's healthy. It will then register itself with Consul. So an important detail with these instances is that they need an identifier. So in this case, I just grab the UUID library, generate a unique ID, and then we use that. When you do register yourself, you want to sort of describe the application. And so one of the pieces of data we need is, of course, the name. And so we'll say that we are a data process. We also tell it the host and port that we're on. So if you can imagine in the world of, like, say, Mesos and Kubernetes. Does anybody use either Mesos or Kubernetes? No one. OK. So these Mesos and Kubernetes allows us to dynamically launch applications, run them on different hosts. So imagine a bunch of different host names running. So I work at OpenTable, and we have maybe 50 different hosts that we run on. So that's 50 different host names. And then each host is able to run many processes on it with all these different port numbers. tons and tons of these processes running. And so there's all these dynamic host and port pairs kind of floating around, and you need to be able to keep track of them. And so that's why we announced that way. Of course, we also want to have an identifier for our instance, our console instance, which we're sending across. And then that check statement is how we define our health with console. There's a few ways to do it, but in this particular example, we're using a TTL check. And what that says is that within every 10 seconds, I will be letting you know that I'm healthy. And then we can run this, this function at the bottom, and we've now registered ourselves with console. And then once that's done, we want to actually perform our heartbeat scheduling. And to do that, it's actually pretty simple. If we've defined a 10-second heartbeat, we want to announce our health within that 10 seconds. And so a good number to go with is whatever you set the heartbeat TTL to. You can divide it by 2. So in this case, we're going to run every 5 seconds. And so what this does is it calls out to the console API. It tells it our identifier. And in this case, we're concatenating the string service : and then our identifier. And then, so we do that every 5 seconds. We're telling it that it's alive, and we're able to keep running. Also in this data service, when the application is gracefully destroyed, so you can imagine hitting Control-C in your console if you're running this application, or if you're using a tool like Mesos, once the process needs to be shut down, it will be given a signal so that it can gracefully terminate itself. So in this case, we're listening for a signal interrupt. And when that happens, we know that we need to shut down. So what we do is we take our console ID, we send it off to the console service, we do this deregister function. And then once that's completed and callback comes back, we know that console received it. Then we can perform a console exit and exit gracefully. And now inside of service www, actually let me back up for a second. Can anybody think of any shortcomings with the deregistration process so far, and that we deregister when we gracefully shut down? What's that?
What if you don't gracefully shut down?
That's a good question. So what happens when you crash? In that case, with our heartbeat set to 10 seconds, that means that between 0 and 10 seconds, our application could be dead and not able to receive requests. And console wouldn't know about it and would still be routing traffic to the host while it's dead. That is an unfortunate shortcoming with the system. So what you can do is inside of your clients is you can implement logic. And so if you make a request to a service, you see that the service does not respond in time, you can then blacklist it temporarily. And then once the next console update happens, you can then start, you get a fresh pool of services to talk to. So that does require some application logic. All right, and now inside of our www service, we need to keep track of all these changes to our data service. And so the code to do this is super simple. I'm just keeping a global array of our known data instances. And so here we perform a watch. So the console API, it's RESTful. It provides a nice way to get all this data from console itself. And so one of the cool features of the API is that many of the endpoints allow you to perform long polling. And so what that means is you'll hit the API, you'll ask for data, and it will sit there and it will keep the request open. And then once the data has changed, it'll give it to you. The connection will close. You'll also be given a magical number, like a token, which always increments. And then you can make another request with that same token. That way, if anything has changed in the amount of time it took you to close the request and reopen, you'll get the fresh, updated data. And so in this case, we're using that watch feature with the console service health check. And so in particular, what we want to know is, we want a list of all these data services with this passing true. And so that means, give me a list of all the data services which are still alive. And now we have this watcher. It's essentially an event emitter. And then so once a change event happens, we'll get a new list of these services. We can simply replace our existing list with this new list and make requests to instances in that list. And the code for that looks, I guess it looks kind of gnarly up on the screen, but it's pretty simple. So all I'm doing here is I grab a random one of the available instances and I make a request to that instance. So previously we'd make a request and it was the hard-coded URL. So in this case, we're just randomly using one. Now you could do something more complex if you wanted, perhaps like round-robin requests through the services. But then you have to keep track of where you left off, and once you rebuild that list, where do you start? But grabbing a random server, I think works pretty good. Cool. But then one day we realized, we should probably scale up our web service as well. What do we do in that situation? And so now we're going to look at the situation where we do scale the web service, and we're going to introduce a new tool in the stack called Consul template. All right, so this tool, Consul template, allows us to dynamically reconfigure config scripts which sit on disk, and then execute a command once the reconfiguration has happened. And so in this example, we'll be looking at more HA proxy, mostly because the config script is small enough to fit on a slide. It's a little shorter than Nginx, but certainly you could use the same functionality with Nginx, with Apache, whatever web service you'd like. So in this case, our script looks a lot like it did before. We define our front end. We're listening for all requests coming in on port 80. We send requests to the www backend. And then inside the www backend, we define this double curly bracket syntax. And so this syntax is called HCL, HashiCorp Configuration Language. It's really simple. You can use it with, again, any kind of configuration script. And so what this does is it loops over all the services labeled www, and then it prints out each one of those lines. So you can think, the range is the beginning of the loop body, that end is sort of the end. We see a new line after the www, and so each one of these entries is printed on its new line, and our configuration script that we're given is nice and human readable. And so the output that we end up receiving is the word server, an identifier of the server, whereas previously we used www1. In this case, it will be those UUIDs that we're generating. We also specify the address and the port separated with a colon, and that's really all we need. And so to actually get this running, we could simply execute the Consul template binary, which again is just a single binary that we can download for our system. And so in this case, we provide it with a template argument, which we then pass a string into that. And so the string has 3 pieces to it. The first one defines that template we saw on the previous slide. The second one specifies the template or the output file that the script will be written to. And then finally, we specify the command that we're going to execute. In this case, we're going to execute this HA proxy restart script. The script is pretty simple. And all I do is print that we're restarting HA proxy. So the command we use for this is we run HA proxy. The -f means here's our configuration file. The -p says write the process identifier to this next file. The -d daemonizes it so it runs in the background. And the last part's really interesting, the -st. And so what that does is it says, hey, use the following PID file. Does everybody know what a PID is? Process ID? A few of us? OK. So every time you run a process on your machine, each one has a unique number which represents it. It's just a way that operating systems keep track of all the processes that it runs. So in this case, since we wrote the PID file to disk, we can then read it later and then use that as a trade-off. So what this does is when each time this is, so you can imagine Consul template restarting HA proxy over and over again as services are coming and going. And so when that happens, it's writing the PID to disk, and then when it restarts, it'll communicate with the previously running HA proxy, and it will ask it to essentially relinquish the port from the old process to the new process. And so if we didn't do that, we would see that maybe every time HA proxy restarts, it's actually blazing fast. It'll run maybe in tens of milliseconds, but that's tens of milliseconds that connections could be coming in and being dropped. So if you have a lot of traffic coming through your system, you want to minimize the amount of packets that could be dropped. And so in this case, it minimizes it. I read somewhere that a request to have to come in at the exact millisecond to be lost. And so this helps minimize the number of dropped connections as much as possible. Nginx has a similar flag as well that you can use for handing off these ports. So some benefits of using Consul and HA proxy is that we no longer have a single point of failure, particularly in this architecture that we've discussed today. There's no single point of failure in code that we own, which makes me feel a little better. HA proxy in this case is our single point of failure, though. If HA proxy were to die, requests would not be able to enter our system. Customers would not be getting the data they're looking for. However, I feel a little bit more confident in HA proxy, at least in the code I personally write. And then, so we're able to easily run our applications on all these different hosts. If you're using Mesos or if you're using Kubernetes or whatnot, you're sharing amongst all these hosts. It's easy to run them all on the different hosts and keep track of them. There are some drawbacks, unfortunately. It's a bit more chatty. We're sending all these heartbeats over the wire. The complexity of our applications are a bit more. We're installing these libraries. We have these asynchronous processes which need to run. We need to keep track of changes in other applications. We need to randomly route between them. Certainly complexity has increased, but our availability has increased as well. And then that issue I mentioned earlier, so your heartbeat, you still have that amount of time in which a service could have failed that you wouldn't be able to properly route your requests. But it sure beats the situation where you only have a single instance running and that has died and then you're just totally dead in the water. Cool, so that's the talk. If you want, you can check out this GitHub link here. And then so that actually contains an entirely self-contained project where you can spin up different data services, different web services. You can run HA proxy. You can run Consul template. These are simple binaries that you just download and you run them with these config scripts. So it's pretty fun. I'll run like 20 terminal windows. You make the requests, you see them coming through, and they route between the different processes. You can kill them dynamically, and they're routing properly. It's kind of neat to play with. And then all these projects that I've mentioned are open source, single binaries, very easy to work with. And of course, I'm writing that book. Does anybody have questions? Yep.
Consul adds its own level of complexity into the solution. Like, at what point does it become worth it?
Yes. So he asks, at what point does it become worth it to add Consul, given the complexity that it adds? If you're a startup, you might not need it. Small companies might not need, service discovery. I suppose once you get to the point where managing your services manually is very painful, or maybe you're dynamically scaling up and down all the time and you want to be able to change this routing dynamically and be able to save money at night when you're not running the applications. And I guess once the existing system becomes a pain point is when you want to switch over. So if you're running fine with a single instance or exactly 2 n instances and you're happy with that, you could skip out on Consul and service discovery. Otherwise, I'd recommend upgrading. Yep.
Yeah, so at work, we use AWS and we use load balancers to do like round robin to our instances. Is that similar to what Consul is doing?
Yes. Yep. So Winston asked about using AWS load balancers to split traffic between different instances. Yes. Yep. They're both pretty similar. So if you use there's sort of the concept of client-side discovery and server-side discovery. So if you do like server-side discovery, the complexity of the routing exists on the server, off the client. And so that approach is good. when you have requests coming in from the outside world and you want to send them to multiple backends and you want to keep the complexity out of the client. That's kind of what the HA proxy layer of this did as well. But once you're actually inside the organization and you have service A that wants to talk to service B, you could send the request through a load balancer and then dynamically hop between. But when you do that, you introduce an additional network hop. You introduce latency into the system. And so if you do client-side discovery, which is the clients asynchronously keeping a list of all the remote hosts, when you do that, the efficiency of the system increases. And so instead of doing these multiple network hops, you can do a single one. Yep.
So just one question, in case the service crashes and you have Sentry loaded on your libraries loaded, is there a way to restart your service? How linking Sentry and your stuff?
I have no idea. I was asking how to use Sentry with your processes, and if they crash, how do you use them to restart? I'm honestly not sure. I'm not actually with Sentry.
Ask the next guy that question.
Yes, ask him. Yep. Anybody else? Yep.
So Consul is itself a distributed system.
Mm-hmm.
Like, what are the pathologies of Consul? What goes wrong with Consul? What will you need to know? Does it ever get screwed up? Does it get wedged? Does it have its own problems you need to know about to run the system?
Okay. Kevin has asked about the sort of the nuances of Consul. What are its failure conditions? How does it break? I have no idea. Honestly, I'm not sure. Like a question, a fundamental question with Consul, I suppose, would be, if one of them is dead, how do you, as the client, when you first connect to Consul, how do you find Consul? I've not looked into that, for example. I'm sorry. Anybody else? Cool. All right, thanks.